I'm hoping it is a good morning for you all, and that you paced yourself last night so that you'd be wide awake and ready for this morning. Day 3 of our symposium. 2 good days behind us. Been a good symposium this year. Had some good positive comments about content, the exhibit hall. So we're very excited about how things have played out this year. I think there's a couple of just logistical things like cell phones, if you can put those on quiet, please, so they don't ring in the middle of a presentation. If for some reason we should need to evacuate, then our meeting or rally point is in front of the Hilton Hotel next door of us to the east here. If you feel like you want to get involved in how this conference is put together and run, please reach out to any member of the organizing committee. We're always grateful for additional hands. It's a volunteer effort, and the more people we have working on this means that everybody else's piece of the pie is a little bit smaller and more manageable. So we have 2 full sessions this morning. We do come back after lunch for a couple of more presentations before we do our awards and wrap up. But before we get started this morning, I'm going to hand off the microphone to Mr. Podkolsky so he can make his announcement.
All right, good morning. Dan Podkolsky, retired, yay. I'm the chairman of the Product of the Year Committee. Part of the process is, since I'm retired for 3 years, I didn't go review any of the products that were submitted, but we did get a good-sized group of experienced professional analyzer engineers who were working in the business, and they went to each of the booths, looked at the product, and we met and provided feedback, and I just moderated the discussion. We, after quite a lengthy discussion, agreed that the product of the year is the Smith Analytical Emissions Master. We had, it was kind of a fun process because I'm just watching these people talk back and forth with each other, and it's fascinating because they're seeing things I never saw before. And one of my colleagues over there, I swear he must sleep with brochures under his pillow. We narrowed it down to 4, and then we kind of iterated through those 4 and came up with this selection. So a certificate's being prepared for Smith Analytical to recognize their award. I think we'll work next year on making sure we can get like a banner so the vendor can or the supplier can put the banner up in their booth at least for the last day, just for additional recognition. So that's what I have. Questions, comments? I feel like I've never been in a rock band, but man, I feel like I'm in a rock band right now with all these lights on me. It's bright.
Dan, we'll put it in the closing slide deck, and we'll give him a certificate. So we'll tell Steve, and I'll put it in the closing slide deck. That's perfect.
All right, thank you, Dan. And thank you for the team of secret shoppers that went around to all of the vendor booths to do the evaluation on the products.
We decided to call it the Analyzer Conclave.
The Analyzer Conclave, very secretive. And but not quite so political as the conclave, I would hope. So that is, the general stuff. We're ready to kick it off here this morning. I'm going to hand over the microphone to the session moderator for this morning, Mr. Rod Meritz.
Good morning. Can we get our first speaker up here, please? Our first speaker is Bill Pearman. He's with Spectrum Environmental Solutions. The title of the paper is Product Manager for Open Path UV DOAS, Retroreflecting Arrays, and Raman. Bill is a graduate of the University of South Carolina, Columbia. He's got a doctorate in philosophy. You must be fun at parties. Analytical chemistry under spectroscopy. He served as a plant forensic analytical chemist for the 3M company, supporting production efforts for two major divisions, and served on the manufacturing forensics network, supporting all production efforts. Previously served as an associate analytical manager and spectroscopy subject matter expert with Dow Chemical as well, and 20 years in the U.S. Army. Bill.
Thank you, sir.
It starts up right there.
Okay. Good morning, everybody. Can everybody hear me okay? All right. Usually being heard is not an issue with me. It's getting me to be quiet is the issue. Welcome, and thank you all very much for taking the time to be here this morning. I know it's the last day, first talk of the last day. At least we're very close to breakfast. That's where I thought I had a good chance of getting some of y'all to come in here and hear what we had to talk about today. So you've heard a couple talks about Raman spectroscopy, and some of the previous speakers done a really good job doing a background of what Raman is and its applications in a little bit of theoretical and some classical explanations of the Raman effect. So we're going to talk a little bit more about that, but I promise not to bore you too much. So brief is italicized because, well, as brief as a former professor can be, I will promise to do that. So first of all, Raman is an effect discovered by C.V. Raman back in 1928. I used to tell my cadets when I was an instructor is if only you could hold a piece of glass up and say, that shouldn't be there, Nobel Prize. Simple as that. Using a mercury arc lamp, he was able to block the emission from the mercury arc lamp, still see a line going through his sample, and that line is, the Raman effect. It will be scattered. Either the photons will gain energy or lose energy. We talked a little bit about that previously. And then the laser light is scattered, and there is no absorption or transfer of energy. That's Rayleigh scattering. We really don't learn anything there, and doesn't provide any spectrochemical relevant information to the sample. So some of you may look at this picture and go, wow, I remember that looks like a gas ion laser. And if you are, you probably got a lot of gray in your beer and up top like I do. This is a good cartoon that shows that the Raman effect. In this case, we have this red laser. And if you want to be totally geeked out on it, I would probably say it's a krypton ion based on the color. And we got this red laser beam. It's interacting with our sample. And you'll notice that most of the arrows are red. And those red arrows is representative of Rayleigh scattering. Red went in, red came out. What did we learn? Nothing. What the energy wasn't transferred to the molecule. There was no vibrational absorption. But what you will notice, there were those two yellow arrows. That is what we're interested in. That is the inelastic scattering, and that's where the Raman effect takes place. And there are two different types of Raman effects or vibrations we look at, Stokes and anti-Stokes, and I'm going to get into that a little bit more. But I got to go to my favorite teaching slide. So what Raman is, it is a molecular technique that takes advantage of this light scattering phenomenon, this inelastic scattering. It does provide qualitative and quantitative information on your sample matrix. It's a relatively weak process, which some of the previous talkers have already mentioned. It is accessible to solids, liquids, and gases. But what is it not? Anybody know what's coming? I was going to go get one and then throw it to anybody who guessed it. So notice slight spelling difference, right? So get this a lot, and everywhere you talk about Raman, it's like, yeah, it's not that. But what it is what we talked about, and we talked a little bit about Stokes and anti-Stokes. Again, if the scattered photon has the same energy, what came in came out, that's Rayleigh, we don't learn anything. And that's indicative of the peak that you see, the big peak in the center. You know, the V excitation there's no change. The anti-Stokes, what happens is that photon actually gains a little bit of energy, and the Stokes, that photon actually loses a little bit of energy. And that gain and loss of energy is responsible for that laser light, or that your excitation energy interacting with that molecular vibration. So just another cartoon, you have your laser energy, it's hitting this sample, you get the green scatter, you get the red scatter, and you get that kind of a brown scatter. Now, the reason that we have this change in amplitude between Stokes and anti-Stokes is where that molecule has to reside before it scatters or inelastically scatters that laser energy. Where are we all right now? We are in the ground vibrational state or ground electronic state because we just got up. Where were we last night at the open bar? Well, we were slightly elevated. We may have been in the ground electronic state. We were definitely in an excited vibrational state. So that's why that delta in your peak intensity between Stokes and anti-Stokes occurs, because you've got that molecule already has to be in an excited vibrational state in order for it to go to this virtual state and back down. Now, virtual state, it's very difficult to explain and to get buy-in on what a virtual state is. But what you will hear is that fluorescence is the death of Raman. And gentlemen talked about fluorescence yesterday and the effects that you see with fluorescence. And those are all true, but the reason you achieve that is because you achieve an excited electronic state, which is that solid black line in the center graph. Once you achieve that, you've bypassed your virtual state. There's no way to get a Raman effect anymore. So fluorescence is something you should definitely avoid at all times in order, if you want to see a Raman effect. So brief in air quotes again, right? So some industrial applications of the Raman effect. Some lessons learned. We focused mainly on extractive. We don't have a strong background in our company on fiber optics. So we do have a good background or a strong experience in extractive type systems, extracted FTIR, and now we're applying that to Raman. Some of the cells that I personally have worked with are we used a 10-meter FTIR cell. My original goal there was just to steal Raman off of a 10-meter standard white cell that we had available. It worked very well. However, the coatings couldn't support the continuous laser radiation of a 0.2 millimeter size beam, and we eventually got into some trouble there with degradation of our reflecting optics. A Herat cell worked very well, but you could also start to see some of the variations in the beam patterns on your mirrors because of the thermal convection that happens inside a heated gas cell. Forgot about that lesson and there was a lot in the literature about near confocal cells. Near confocal cells, the beam comes into the cell at a very sharp angle. It hits a couple mirrors. It forms two focal points. So you have a very high power density, and if you come in from the side, a 90-degree collection, you can cover both of those foci, and you get a very high laser density, very high scatter density, and very good limits of detection. Until you heat it up and you get the thermal convection inside the cell again. Now you have this multiple beam paths being altered by this change in the indices of refraction of the gases because of the thermal effects and convection. So didn't work very well above 35C. So how to keep it simple? The simplest design is a dual pass Raman cell. The light goes in, the light comes back out. There's two ways to collect. You can come in from the side, which we call a 90-degree collection, or you can collect from the back, which we call 180 backscatter. Which is the easiest? That is the easiest way to go. Okay, so we have this experience. We've tried these different things, trying to drive down limits of detection. It works, difficult to maintain in an industrial environment. So how do we achieve both? Well, focus on this dual pass cell. Now, most of the talks you've heard the Raman, right? It's an instrument, it's an entity. It is an entity, but it's an entity of individual components. And that component selection is critical to the success of the overall analyzer. It's not the Raman, it is the spectrometer, it is the laser source, it's the laser wavelength, it's the filtering optics, it's your spectrometer, it's your grading. There's all those components that just kind of get lost in the instrument or the analyzer. So I decided to take a strong look at those individual components and see where we could eke out a little more energy, eke out a lot more signal, reduce our noise without having to go to some exotic multi-pass type cell. So some of the constraints, I want to keep that 180-degree backscatter. Why? Because it's easier to maintain that alignment. Again, just think if you're trying to come in from the side and stare at a focal point of a laser at all times, that is a lot more difficult than the beam is always in line with your collection optics. And I'll show you a little schematic here that'll make that a little more clear in a second. Can't step on my $7 DG reading glasses. If you ever get LASIK, talk to me about it. It's not worth it. You trade one set of glasses for 5 sets of other glasses. This public service announcement, that's free. So some of them else we want to talk about is, the spectrometer itself, getting that light to it. We're going to maintain the fiber optic. That way you don't have to worry about the collection arm being continuously aligned with the slit of your spectrometer. And then the spectrometer itself. We've used one spectrometer. It's probably the same spectrometer you think of when you hear miniature spectrometers, same company. But we started coming into some trouble with some of our other systems, specifically our OpenPath UV DOAS system with changing models. So we started looking around at what other miniature spectrometers were out there. And so we started finding some others, and I wanted to compare and contrast at least 2 of those, and that's the data I'm going to present here today. The filters and the beam splitters, plenty of options available to us out there. So what we want to look at is a design similar to this little cartoon. So the laser located down here is a 532 nanometer laser. I prefer the green because hydrogen is one of our target species. Yes, you can go after different bands using 785 nanometer laser. And the Raman shifts are all relative to your excitation wavelength. So it's always the same number, but on the nanometer scale and where that is, it's always shifted relative to your excitation wavelength. I prefer to go after the fundamental for hydrogen, which is at about 4,500 wave numbers. Can't see that if you use 785 excitation because it puts it too far out into the near infrared for a standard CCD type detector to be able to pick it up. So we start with a 532, the beam comes out, hits a 45 degree turning apparatus, passes into the cell to where we have a little beam splitter. The beam splitter is a 70-30, reflects 70% of the laser energy towards L1, which is our first focusing optic, focuses to the center of the cell. The beam then continues on, diverges to a concave mirror set at 2F distance from the focal point, so it refocuses back through, goes to the beam splitter, and this is where the magic happens at the beam splitter again. Now here, we're not interested in the Rayleigh scatter. Remember, green in, green out, we didn't learn anything. The hits the beam splitter this time is redirected back toward the laser. However, that longer shifted Raman or spectrochemical relevant information passes through your beam splitter. And then it is collected by your focusing optic. There's a notch filter there. I've looked at notch filters, long pass filters, razor edge filters. I guess my company's tired of me spending money on filters, but it's critical to get rid of that scatter that's coming back towards the fiber optic where it's actually ultimately focused into a fiber optic cable and then taken to the spectrometer. So the spectrometer itself, there are 2 different spectrometers that I used in this case. There's some of the information up there. I apologize to people in the back. I know you can't read that. There's 3 black blobs on the screen. But just know that one of them is half as much as the other. That's what everyone kind of focuses in on. But the other critical thing is that spectrometer A, as I'll refer to the rest of the talk, has a grading that's blazed exactly where I need it to be. It's blazed in the green, about 540 nanometers. The other spectrometer B has a grading that's blazed at 750 nanometers, so non-optimal. So all the quantum efficiency curves you see here on the bottom graph, just think of those shifting to the right, because that's really what I'm dealing with in this case. But it's what I had, it's what the vendor was willing to provide me without cost, which is always key to me and our company, so that's what I went with. So non-optimal, but let's see how it performs. Let's see how it outperforms against different fiber optic arrays. We had been using this configuration, 7 fiber optics in a round configuration, which is at the collection end of the system. The vertical linear array goes and lines up with the slit of the spectrometer. Most slits are vertical, so you can put 6 or 7 fibers worth of light against the slit, and you can get higher signals, so it should be better. Should be better, okay? And we also looked at single core fibers. So the reason I say it should be better twice, because it's not always the case depending on how your internal optics of your spectrometer are arranged. And there's a difference between A and B, and I think you'll see it come out in the data here. So I'm just gonna go quickly through here. Again, this is an eye chart, and I apologize, I had no idea this room was this big, but there's a couple of things to focus in on. What I did was I took just compressed air, put it into the analyzer, I chose the different fibers, and optimized each individual spectrometer, ran the oxygen and nitrogen through it from the compressed air, and then looked at the quality and reproducibility of our oxygen and nitrogen peaks as a function of not only spectrometer, but also of fiber. And one thing I noticed was that in spectrometer A, the standard deviations between your peak heights were a lot larger than what I was seeing in the other spectrometer. Now you're gonna say, well, that's because you're getting more signal, which you can see here as well, and that is true. But I still kind of focused in on that. It's like, one problem with multivariate analysis techniques is if your reference data is set to a certain standard deviation, and then you're getting data that's bouncing around that, it's gonna see that as a change in concentration, which is not necessarily the case. These are all continuous concentration, continuous flow. So I kind of zeroed in on that, and I wanted to see what it looked like. But let's first look at the signal to noise, because that's what it's all about. Everybody says, get big signal. Yeah, if you have big noise, it doesn't matter how big your signal is. The key is managing your signal to noise ratio. And if you look at these numbers, it looks like spectrometer A is a clear winner here. But what caught my attention was when I took all this data and put it into principal component space. Now, principal component space allows you to look at a multivariate analysis technique where it takes a lot of the variability to data and breaks it down into somebody like me, a Cro-Magnon knuckle dragger, can understand. It's principal component 1 in this case, which is your bottom axis, is your change in your peak height as a reflection of concentration changes, okay? But what's principal component 2, your vertical axis? Principal component 2, there's a thing called the loadings. It's not a true representative of the spectrum, but it does give you an idea of what's causing that shift. And then what's causing principal component 2 in this case is spectral positional shifting of your peaks. So if you notice, it looks like these are pretty good. They're pretty equal in terms of both X and Y variability. But what do you notice on the scale? Quite different. So I said, okay, let's put it on the same scale. So putting it on the same scale, spectrometer B does not exhibit the same amount of spectral shifting on your x-axis, nor does it also have the same amount of variability in peak height. Well, that's pretty important, as we talked about a few minutes ago, in terms of the robustness of your spectrochemical models. I say, okay, same thing here. Going to a 50 micron slit, good signal to noise. You can see spectrometer B is starting to gain a little ground. But again, look at the scale here. It's a factor of 10 difference. So that kind of intrigued me on how this might be a better approach to our spectrometer selection, even though it's not optimized for our laser wavelength. So what are some abilities? Who cares about, well, I know we all care about oxygen, nitrogen, or we'd be, doing the kicking chicken right now, right? But in terms of spectrochemical relevant information in your process, maybe you care about other things. So what we decided to do is take some blends and some hydrocarbons and evaluate the spectrometer's ability to look or differentiate those different hydrocarbons. It was 9 different hydrocarbons and nitrogen and hydrogen in these blends. And you can see that the correlation curves are really good. Now, how did I develop these correlation curves? You build your reference data set, you validate your methods on that data set. That's called verification. And then you run an entirely new data set through it. I call that validation. The first, if you want to stay that way, I call it cheating. You're using the same spectra that you use to develop your method to validate your method. Okay, that's a little iffy. But come back the next day, throw something different at it, see how it performs, and then conversely, later on, continue to throw additional fresh runs at the model to check its robustness. Calibration error is all pretty good, all south of 5%. So both of these, again, look to be pretty good in terms of their ability to differentiate and quantify at least the 9 species in these 3 blends. What if we wanted to use this to determine your net heating value? How well would these 2 spectrometers be able to perform in that application using the EPA's PS9 evaluation criteria? Well, luckily, we have a consulting group that had all these calculations in a single spreadsheet, or I would really bore you to death with my Excel abilities to produce graphs. So here is the PS9 results from spectrometer A. And what do you notice about that besides the red? All right, the red was where it did not pass. There, the requirement is 0.995. It came close, 0.993, but why did it fail? If you look at your reproducibility, you can see those numbers change from the first blend to the second blend, and we are sitting about 1% or so in precision, but if you look at the calibration error, it's sitting around 1 to 3. And again, why is that? Because not only is the peak shifting on your x-axis, but it's also shifting in your intensities. Now, solve that with TE Cool? Yes, it does have a TE cooler. So I think that it's pretty much approaching its limits in terms of reproducibility, but how did spectrometer B perform? Now notice not only the calibration error, but the precision and also the linearity is also where it needs to be. So what I observed going through this systematic process was this change in peak intensity, which actually turned to be not only a change in peak intensity to constant concentration for a given spectrometer, but also some wavelength shifting. Now, our software package does allow you to correct for that shift. I did do that, but that's an extra step. The more extra steps you put in, the more chance of human interaction, the more chance of over-massaging the data or coming up with something that is not representative of your original measurement. So I try to do as little to the data as possible, just as a general rule. And so this seemed to be a much better approach, a way to go. So some summaries. Really think that this 2-pass cell is going to be the way to go. It does have the limitation, if you want to call it, of bringing the gas to the sample, but you can either run fiber lines or you can run gas lines. Either way is the way to get the information out of your process. Now, these detection limits that I put up here, 0.75% to 0.1%, these are what I call the red face limits, right? I could stand there and get yelled at all day long and say, yes, I can see that. Yes, I can see that. Can I see lower? Yes, we can see lower. It's very dependent on your molecule, your compound of interest. Some people mentioned about, I don't know if they mentioned it or not, it's called the Raman cross-section. In terms of cross-section, that's the ability of that molecule to scatter your Raman signal so you can actually pick it up. Now, liquids, very easy. Solids, even easier than liquids. Where gases, way over here. They're very difficult. Why? Because your molecules are spread apart. There's not a lot of intermolecular interactions. So it's very difficult for Raman and gases. As a matter of fact, when it first came out, it's like, just don't even bother. But we've advanced our lasers, we've advanced our spectrometers, we've advanced our optics, and that's why you're starting to see a little more conversations that involve Raman. Compositional analysis within 10%, yes, I showed 5. Again, this is red face. You know, you can yell at me all day long, and I'll say, no, yeah, I'm 100% sure it's plus or minus 10%. 99%, it's 5%, but just as a general rule. So the changes that we have made, and I'm going to show a little cartoon of what it looks like here in a second. The changes we have made are all experience-based. They're not the crazy guy in a tie-dye lab coat in the basement coming up with ideas, which is a benchtop instrument that we're going to throw into a process. That was me. Okay, I did do that. I did have a tie-dye lab coat. It went very well at the United States Military Academy, if you can imagine. It didn't. But I still wore it because it's who I am. What we have done is taken all of that 100-pound brain stuff and applied it to how make it simple, make it simpler, make it more efficient, make it as good as it can be in terms of limits of detection and reproducibility. What's the end goal? To get this amp. We met last week. We've generated the request. We're sending it off to EPA, focusing in on the net heating value, but also with your component ability, your individual component ability. And we hope to get this approved soon. And that will go a long way to assuaging any angst out there about using this technique or this capability. We're ready to go. We're ready to build it. We have the instrument that I used to collect all this data down in our booth at 627. It's a lot. Again, we learned a lot from that. We made it a lot simpler to get to things, and also cooling and instrumental purge. That was on my slide before, because you do pick up Raman scatter from ambient nitrogen. That gives a little variability that we can eliminate by eliminating that air background inside of the analyzer itself. And if you compare and contrast what this looks like to what our analyzer looks like down at the booth, you'll notice this is a lot simpler, a lot more access, and a lot more easy to maintain and to keep aligned. With that, I thank you very much for joining me this morning. Appreciate y'all coming in and hearing what we have to say. And if you would like to come down and beat me about the head and face about things that you didn't like I said, come on down. I'll be down there for the next hour or so, and look forward to chatting with anybody or answering any questions. Thank you.
Thanks, Bill. Do we have any questions about the presentation? A very question-free audience. Thank you very much.
Thank you, sir.
Appreciate it. Our next presenter is John Calame. He's with Anderson Hauser. He's the market product manager. He graduated from Texas A&M with a BS in industrial distribution and the University of Houston with an executive MBA. He's held a variety of sales management, marketing, and product marketing roles for Emerson, Yokogawa, ABB, Servomex, SICK, and E&H. You just got to come work for Amatec and you'll have the holy sextuplet. Hobbies are reading, exercise, gardening, cooking, hunting, and fishing. And
thank you.
Let me just switch out the presentation. Timer's in the upper right-hand corner.
All right. Now, everybody awake out there? Everybody ready to talk about particle size distribution? Alexander, R&D manager, who is the father of this technology. We thought he would be here to do this presentation, but unfortunately, or fortunately, we had an opportunity to put in a trial unit in the United States, and that happened last week, and it was very successful, which is a good thing. But the bad thing is he had to get back to Germany because his wife was traveling this week, and so he had to watch the kids. So All of a sudden, I became the presenter of the presentation, so I'm going to do my best and try to do it justice, but pray for me.
Turn on here.
Houston, we have a problem.
Full battery?
I can just use the.
Yeah, if
I
you
guess.
don't mind, just use
Is it down?
the arrows. Or down, doesn't matter.
All right, cool. All right. So filtration companies have done a fantastic job of developing filters to filter out particulate. So kind of a victim of our own efficiency of technology with filtration, because you've removed the larger particles, but what remains is the smaller particles. And the smaller particles are more dangerous to humans because you can ingest them into your lungs further, and it causes problems like COPD or emphysema, and ultimately, degradation to cancers and death and things of that nature. It's not a good thing to have in the atmosphere. So to just kind of go through a few terms here, typically the PMCEMS and where our target market is coal-fired power. So I don't want everybody to tune out in here, because there's probably not many people in here that's in the coal-fired power business, but you might want to stay tuned in, because some of these regulations may migrate and make their way to the industrial marketplace. But typically we use an AMS, which is an automatic measuring system, and in this instance it's a PMCEMS, so it's a particulate matter continuous emissions monitoring system that's on the stack 24/7, collecting data and reporting it to the EPA. But we also have to compare that to a standard. So the standard reference method, the EPA prescribes method 5 or method 17. They're both gravimetric standard references, and so we have to reference our optical technology to that and do some correlations. And because of the uncertainties of those measurements, you have to make many measurements and then average those together. There we go. So here's an example of the gravimetric reference. We compare that to the optical particulate monitor, and then make sure that it correlates properly. So we can use method 5, which is out-of-stack measurement, grab samples, or an in-stack method of measuring the gravimetric standard. It has to comply with PS 11, Performance Specification 11, outlined by the EPA. So you have to do multiple iterations and average those out and make sure that it's reacting properly. And the PS 11 correlation testing usually takes 2 to 3 weeks to do. It's very involved and very expensive. So this is showing different size particles from 3 micrometers up to 15 micrometers. And light scatters differently, is affected by different particle sizes, and usually optical measurements take an average size. So if you have a lot of large particles versus small particles, it can skew your measurement. So if you had a filter break, for example, and you had an average particle size increase that was due to maybe having a few larger particles versus smaller particles, you could end up under-reporting the total PM particulate monitor loading. So here's an example of some of the filtration technologies. On the far left, there's an electric static precipitator where they charge the electrical plates to create a static charge, and it attracts the particles, removes them from the stack. Very, very efficient operation. Then on the right-hand side, we've got traditional mechanical bag filters. So you have fabric filters that will filter out the particulate. Once they get full, either there's a mechanism to empty them automatically, or sometimes they have to replace the bags. But if you don't pay close attention to it, the bags can rupture, and then you can get a spike of particulate matter going up the stack. If you have an issue with a problem because there's the larger particles and you don't know how many of them there are, and you get an inaccurate reading, then your ESP, there's a signal sent to the ESP to ramp up that power to make it more effective, and it really didn't need to, because it's unrealistic or not a true particulate loading. It's a false reading, but it causes your ESP to work a lot harder than it has to, and uses up a lot more power. So our proposed solution, and this is an emerging technology, I can't sell you one of these today. We've been working on this for several years, but it did escape from the lab. So we've got 10 industrial demonstrators that have gone around the world and been put into applications, various applications, a lot of them in power industry, but we're looking for other industries as well to apply the technology. But what if, instead of just getting a total PM number, particulate matter number, you could get, know exactly what the sizes are and the concentrations of those individual components from 0.1 to 30 micrometers. So this is what this technology is designed to do. So it uses UV wavelengths of UV to NIR, so it has multiple sources of light, and also has multiple highly sensitive detectors, and then some mathematical modeling to come up with the PSD levels. But it's still, initially, it needs to be referenced to the, SRM, the reference method initially, but the hope is that we get the EPA to buy off on it, that once you've done this initial calibration, now you're measuring it, making a direct mass measurement continuously, so you'll not have to do those testing on an annual basis, which is something that we haven't got that approved with the EPA yet, but they're looking at the trial that we're doing in the U.S. very closely. So that would be a game changer. That would save the industry a whole lot of money. So on the top is the actual sensor housing. Then we've got a purge air unit, and then the bottom picture there just shows a shroud that goes around it to protect it from the elements. It's a close-coupled extractive design, so you only have to have one flange, so it's easy to install on the side of the stack. Very, very easy to. The unit that was installed in the U.S. Went in, and one day they had it installed, commissioned, and up and running, so very easy to install. We've only run, had 1 year of run time at one location, so cleaning intervals are gonna vary as far as the optics, but in that 1 year trial, we did not have to clean the optics. And then we did the dry gas version first, and then now we're developed a wet gas. So the wet gas one that we started up last week uses a little different technology. Same basic sensors array, but there's a additional thermocyclotron that actually removes moisture. It takes the sample, drives off the moisture, and then takes it to the optical measuring chamber. So the wet gas unit that we're working on, we're hoping that will be a great success, because there are a lot of coal-fired power plants that in the U.S., 80% of them are wet gas, and unfortunately the first one we developed was dry, so they retooled it and came out with the wet gas so that we could go after a bigger market size in the U.S. So there's a thing called the MOTS rule. It's a mercury air toxics regulation that came out in 2024, July of 2024, and it reduced the permissible level of particulate by 1/3. So it went from 0.03 pounds per million BTU down to 0.01 pounds per million BTU. So it's inherent that you continue to push the envelope and develop new technologies to get to lower levels of concentration, as well as the PSD gives them some additional information to be able to modify their filtration technologies to stay ahead of the EPA regulations. And I apologize for this particular diagram here. This was a test that was run about 6 or 7 years ago, so they couldn't recreate the data for me and be able to separate it out and explode it up and give us a good, clear view of what's going on here. But the blue line is the opacity from the existing optical opacity meter that's measuring total or particulate level, and then the red line is the PSD total particulate, and it tracked, perfectly on the total line. But what the PSD gave you was it actually gives you the concentration of the individual particle sizes, the PM 2.5, 10, and the PM1. And so what it displayed and what it was able to show a richer data set. So now they could tell that almost all the particles were below 10 micrometers. 50% of them were smaller than 2.5. So it gives them some information that they need, necessary to modify their filtration strategy to make sure that they eliminate those smaller components. So in conclusion, we are demonstrating this emerging technology for PMCEMS. It'll be a revolutionary device that, if approved in place and the EPA approves it, will reduce the cost to industry to, do the annual testing. If you can do the first test and then let it run, for forevermore, and be confident that you can get the PSD, the PM1, the PM 2.5, and PM10 particles concentrations continuously, will help the industry, because that MOTS rule that came out, there were hundreds of power plants that were grandfathered and only had to do annual testing, but now they have to put in continuous PMCEMS. So they'd like to move to the next generation, which gives them a much richer data set and ability to modify their filtration strategies to stay ahead of the EPA regulations. So it's a close-coupled extractive design, so there's no need to, align optics. Everything's pre-aligned. It's very easy to install. From an expense standpoint, it's minimal and very convenient. Uses a scattered light principle and multiple, wavelengths of light, and several highly sensitive detectors and mathematical algorithms to make that continuous PSD measurement. And like I said, it escaped from the lab, so we've had it lab testing around the world, and also 10 industrial units that have been put in the field, grabbing empirical data to refine the design. And then we're still looking at other markets like chemical, petrochemical, refining, and fertilizer to put additional demonstrators in to prove the concept. And so this gives you, the industry, a PSD tool to help you minimize or eliminate, hazardous air pollutants from, particulates. And that is it. Any questions?
Thanks, John. Do we have any questions about the presentation? I guess I have a question. Would this be applicable to municipal waste incineration?
Yes.
That sort of thing?
Yes.
Yes? And do you intend to kind of target that market?
That's not one that we have talked about, but waste is cement is a target market, and as we all know, cement is kind of like they get extra money to incinerate medical waste and tires and things of that nature. So anything that burns and produces particulate matter would be a potential target.
Thank you very much. We have a speaker's gift for you here. And Bill, if you're still in the room, I apologize. I forgot to hand you your speaker gift, so if you could come up and get it. And as well, we have our next presenter. Ryan Sheehan from Canty, if you could come on up. Tod is not able to make he was supposed to be the presenter and is not able to make it. So we're going to have Ryan present in his stead. So you're going to have to use the left-right button. I did close out the presentation, but it doesn't seem to have made any change to this. So just
Okay. Good morning, everyone. Thank you for joining me today. Unfortunately, Todd couldn't be here to present, so I'll try to fill in his shoes. My name is Ryan Sheehan, and I'm an applications engineer with Canty. I graduated from the University at Buffalo with a degree in chemical engineering. I was born and raised in Buffalo, which is, very cold. Hobbies, I really like to golf, but as mentioned, from Buffalo, you only get 2 months of the year to be able to do that. So today I'll discuss Canty's lab and online detection of off-color materials via dynamic imaging technology. So here's a quick outline of what I'll be discussing today. First, I'll discuss why Canty developed a system to be able to analyze this. So what is the need to monitor processes for off-color materials? Then I'll give an introduction to vision technology and dynamic imaging, which is the principle of the analyzer I will be discussing today. Next, I'll dive into the core mechanical design elements of Canty's dynamic imaging analyzers. Then I'll go over a few different case studies of off-color material analysis and wrap it up with some conclusions. So what is the need to monitor processes for off-color materials? First off, off-color materials are present in many different industries around the world. Applications can be from crumb rubber plants, which I will be discussing in the case studies today, all the way to the food and beverage industry where you have stereo pellets that need to be uniform and consistent in color. There are a variety of causes of off-color materials. These can include impurities from raw materials, environmental conditions such as temperature, humidity, light, and pollutants, as well as general process control problems. Off-color materials present a major quality issues for companies. If they're able to identify this, they're not able to ship off their product to the customers. This is why it is very vital to identify and quantify the presence of off-color materials. If you're able to identify when and where these contaminants occur, you can potentially save entire batches of product from needing to be scrapped or reworked. So here's an introduction to vision technology and dynamic imaging. As I mentioned, dynamic imaging is the basis of our analysis, which utilizes a camera and light to take constant images of material as it flows between the camera. This technology is used in a wide range of applications across many different industries. Other examples of applications where dynamic imaging can be used are for monitoring, for example, a produced water stream where you're trying to pick up on oil and TSS in the water stream. With dynamic imaging, Canty is able to provide both concentration and oil droplet size, which is very important for being able to efficiently separate oil and water. Another application we can do is monitoring the foam in tanks, if you have any foaming tanks or vessels. Based on the intensity of light that the foam emits, we're able to set a certain threshold and communicate with your control system to inject anti-foam once it reaches a certain level. This is a major cost savings opportunity because operators are constantly injecting anti-foam because the only way they get in trouble is if you have over-foaming in the vessel or tank. So going back to this specific application of off-color material, dynamic imaging has to be able to determine the difference between bad material, good material, and background material, which in this case is most likely going to be a conveyor for crumb rubber. We also need to be able to quantify the amount of bad material. This can be count of particulate that is off-color, as well as size or shape of the off-color material. Finally, we need to be able to output the data, especially for inline systems. We are able to output via Modbus, OPC UA, or 4-20, as well as a couple different options to be able to communicate with your control system for complete control. So now I'll go over some of the core mechanical design elements of Canty's dynamic imaging technology. The backbone of all of our technology is our fused glass. To make fused glass, we heat glass up to its molten level and flow it between an outer ring. As this cools, because of the coefficient of expansion of the metal is greater than the glass, the metal will create a uniform radial compression on the glass. This creates a hermetic seal between the metal and glass, which protects the camera and lights, which are the external electronics. With this fused glass, we're able to withstand high temperatures and pressures without sacrificing any of the image quality. There's also an option to encompass a jet spray ring with this fused glass to ensure that the glass optics stay clean and free of any debris or contaminants. It's hard to see on the image, but the spray ring is on the bottom right corner, and there are tiny holes in it that emit high-pressure fluid, which is used to clean the lens. This fluid can be anything pretty much compatible with the process. For dry applications, we'll typically use air or nitrogen. For any liquid applications, we can use water, IPA, a solvent, or, as I said, pretty much anything compatible with the process. The spray ring is great because you can minimize maintenance requirements, so you don't have to go out there and manually clean the system, and therefore you can keep the system operating continuously without having to intervene with it. So now I'll move into the lighting design. At Canty, we say that there are 3 keys to a quality image, 1 being lighting, 2 being lighting, and I'm pretty sure you can guess the 3rd, which is also lighting. With inconsistent lighting, you'll get inconsistent imaging, which in turn has inconsistent analysis. Canty has developed a LED light with a fiber optic bundle. This produces a constant, consistent white, bright light. But this also has minimum maintenance, as the light has a lifespan of over 5 years. And as I'll dive into on the case studies more, oftentimes multiple lights are used at different angles. This will eliminate any shadow impacts to ensure that the images stay clean and clear, and this way we can perform accurate analysis with our software. Finally, the last part of the core mechanical design is the camera optics. Canty has different camera optics that can be used depending on your specific application. We'll pick one to make sure that you have an adequate view angle to ensure that you're getting the whole field of view for whatever your application may be. Each Canty camera optic has a certain pixel scale factor, which is the number of microns per pixel. For the specific application I'll be talking about today for off-color material, we'll select a pixel scale factor that is small enough to be able to pick up on all required color contaminants. So now I'll dive into the case studies. The first case study was performed at a crumb rubber plant. This was a lab analysis study. Their typical method was taking samples and analyzing them just by manual inspection and counting contaminants. Just a little bit of background. The cause of the bad color was typically due to the drying process of the crumb rubber. During heating, oftentimes particulate would get stuck on the wall, and as it stayed there, you would get some color change from the white crumb rubber, which is supposed to be, to yellow and even sometimes even black. So just a quick couple points on lab analysis, which is the first case study. Lab analysis, it's a great concept, proof of concept of the technology and getting familiar with what it can provide, but it has certain limitations that will prompt a user to move directly inline later. One limitation is that you're not getting constant analysis. You're only looking at pulling samples from a certain point in the line, and you're making an assumption that that's a true representative of the process as a whole, which we all know is not going to be the case. A second limitation is you're getting a slow response time. For this specific application, they had someone go into the field, obtain a sample, run it back to the lab, prepare the analyzer, run the analyzer, and then analyze the data. By the time you analyze the data and pick up any off-color material, the bad material has already made its way to a bale, and I certainly wouldn't want that job of trying to determine which bale has that off-color material. And oftentimes, this can result in them throwing away many bales because they don't know which specific one had that contaminant. So this image shows the Canty lab system that was used for this analysis. The camera and light were mounted above a vibratory feeder. As you can see on the right hand of the image, there is a funnel that the samples were loaded into. The funnel leads to a vibratory feeder where product was then moved under the camera and light combination. As product was moved under the camera and light, constant images were taken and analyzed. It tends to tougher for analysis. For this application, results were expressed as a count of contaminants in different size bins. We're able to get particle sizing based on the pixel scale factor that I previously talked about. And bin sizes were chosen from 0 to 12 millimeters in 1 millimeter bins. So software is trained to identify variations of good material versus background versus bad material. To do this, we use the intensity of the light of the material, and we are able to set certain thresholds in the software to pick up on certain colors. The images shown here show the software trained to pick up on black materials only, as shown on the left-hand side of the screen, versus all off-color materials, as shown on the right-hand of the screen. So basically, we get certain thresholds in the software that'll pick up on certain select colors. So for this case study, the first test involved running a spike sample 3 times as a proof of repeatability of the analyzer. It's hard to see in the table, but results show great consistency and proof of repeatability of the analyzer, as the 3 different trials had pretty much exact total counts of particulate. The graph on the right shows the bin sizes that each of the trials had for off-color material. As you can see, the results are pretty consistent for this as well. There's some minor variability, but this is due to orientation of the particles as they present themselves in front of the camera. So after proving the repeatability of the instrument, a second test was involved running 10 samples that were taken over a span of a week of process time. As they were run through the analyzer, they were compared to the plant's manual inspection of the material for off-color material. The analyzer showed consistent results with their manual inspection, as we were within plus or minus 5% of their manual inspection. This table brings another point I wanted to make about lab analysis and its limitations. It's hard to see, but you can see sample 8 had a total count of 127 particles that were off-color material. The rest of them didn't have nearly as much, but because you're not sampling all the time, you don't know that between sample 3 and sample 4, for example, there could be a spike in off-color material, and you wouldn't be able to tell because you're not sampling continuously. So with that, I'll dive into case study 2, which was used at the same plant as in case study number 1, but measurements were made directly online. As mentioned before, the desire to measure online in real time allows for constant measurement, and you can also make instantaneous response to any issues with off-color material. For example, when off-color material was detected, we were able to communicate with the control system and redirect that specific material to a waste location until the analysis showed that there was no longer any off-color material present in the stream. This shows our apparatus for the inline system on the right-hand side of the screen. You can see that there are 4 LEDs lights used around a central camera on a mounting plate. This mounting plate was mounted over a conveyor belt. As mentioned previously, the LEDs were sort of set at different angles, and this helps eliminate shadows so that we're getting clear, bright images that can have accurate analysis completed on them. This setup used the optional spray ring to ensure that you have a clear-cut image and not have any debris or contaminants build up on the glass. And the results were similar to case study 1, where we looked at the count of contaminants and also have deep bin sizes. So once again, the software had to be trained to look at variations of good material versus background versus bad material. The images shown on the screen show examples of contaminants detected by the software. You'll see on the left a brown contaminant, and you'll see on the right-hand side of the image a black contaminant. This makes another key point about dynamic imaging. With dynamic imaging, you're able to record videos and look back at them later. So if you want to rerun analysis based on picking up on different colors, you always have that option. This slide shows the results of case study 2, which was for online chrome rubber analysis. This data was obtained over a 24-hour operating window. The y-axis represents the particle counts of off-color material, while the x-axis represents time over the 24-hour window. As you can see, there were certain spikes throughout the day due to off-color material being detected. With the ability to communicate with the control system, bad material was successfully detected and redirected in approximately 8 different instances over this 24-hour window. The third case study differs from the first 2 in that it wasn't with chrome rubber, it was in a plastic plant that produced plastic pellets. At one point in the process, there's an extruder that has strands before they're cut into pellets. At the outlet of the extruder, it was observed that you had some off-color strands for short durations of time. The plant confirmed that this wrong color was typically either due to issues with the raw materials or some sort of process upset that they had. The issue is with the speed that the strands were exiting the extruder, it was very difficult for a person to be able to manually inspect and determine off-color material. However, with the camera system that has a high frame rate, we're able to constantly take images and then send them to software for the same analysis that we did with the other 2 case studies. The apparatus for this system is similar concept to the first 2 with slight differences. This just used a single camera and light that were mounted above the outlet of the extruder. This camera also included the optional spray ring to ensure that the view stayed clear and consistent. And instead of expressing the material as just a count of contaminants, this case study expressed it in terms of area. As I mentioned, we also have the ability to do particle sizing based on the pixel scale factor that we set. So for this case study, we took advantage of that and expressed the bad contaminants in terms of area. Since it was difficult to easily replace, we actually trained the software by placing bad strands of material on the extruded fibers. Examples of these can be shown on the screen here. For example, on the left side, you'll see a dark brown contaminant that we put onto the extruded fibers. The image on the left side shows the raw image that was taken, while on the right, you can see that green box, which means that the software is identifying that contaminant. And this is the same exact situation on the right side of the screen for a yellow contaminant that was also placed in the extruded fibers. So the results of case study 3 were similar to case study 2, where we had a 24-hour operating window where we plotted the area of the contaminants versus the time. As you can see, again, there was select times during the day where you had bad material that was successfully detected. With this, we were able to divert this material to waste. So here are some conclusions of the presentation today. So dynamic imaging continues to grow and can be used as many different industries and processes for process control. As mentioned today, we can use this, for example, of off-color material to detect it and divert it so that you're not having those quality issues that you can receive complaints about from customers. Data can be output and quantified in many different ways, such as raw material count, which we discussed in the first 2 case studies, as well as any sort of size or shape distribution as expressed in the last case study. Canty has the ability to provide both lab systems and online versions. As mentioned, there are some limitations to the lab analysis, as you're not able to constantly analyze samples and you don't have instantaneous responses as you do with online systems. Overall, this is great to put this in line at one part of the process, but the great thing about dynamic imaging is you can put this all over the process and monitor it real time and really see where you have process upsets and make changes in real time to optimize any sort of equipment or process that you have. That's all I have. If you have any questions, please feel free.
Thanks, Ryan. Do we have any questions? A question-free crowd. All right, thank you very much. Appreciate it. And that ends the first session this morning. We will restart at 10:30, so go have some coffee and check out the exhibits. Thank you.